Alright, hello everyone. I'm going to use this video to explain to you the background related to this lab and to also explain the data analysis that goes along with it. This lab is really an important lab. The topic of drag is something that we have not talked about yet, and it's one of those unique topics to AP Physics C that we did not do last year. Everything in the topic of drag relates back to the dropping the coffee filter lab. So it's really, really important that A, we do the lab, and B, that you understand the data and the data analysis behind this. So I'm going to start to explain the background related to this, but I'm also going to keep one eye on the clock. And if the video starts to get too long, I may just stop it abruptly and then do a part 2 so that I know that I can upload it later. Okay, so first of all, make sure you have your lab sheet kind of handy and that you have some scrap paper here so that we can talk about this. All right, this lab is about coffee filters, like just plain old coffee filters. And so I have a pile of coffee filters that I got from school, and I took out 7 coffee filters that are stacked, tightly stacked. So like I made sure they weren't separated, but I kind of peeled a little bit to make sure that I had 7 of them there. All right, so I'm going to set them off to the side. All right, the purpose of this lab is to see if dropping coffee filters, if the drag model, if the drag acting on coffee filters is proportional to a velocity or a velocity squared. So again, in the notes we talked about the different drag models. And so a drag model usually is proportional to just a v, meaning it's a linear model, or it's proportional to v squared, meaning it's an exponential model. But honestly, it could be any v to any power or v to anything. But these are the most common ones. I would say 95% of the time it's one of these two. Second thing we're trying to find out is what is the coefficient of drag of a coffee filter. So when I say what's the coefficient of drag, that's kind of like how aerodynamic are coffee filters. If something is very, very aerodynamic, the drag force on it would be 0. Okay, that's the best you can have, like no drag at all on it. But that obviously is impossible. So just like coefficient of friction tells you how slippery something is, the coefficient of drag is going to tell us how aerodynamic the coffee filters are. So we're trying to find out what kind of model, and then use that model to find the coefficient of drag. Okay, so we're going to start by looking at the 2 drag models here. So one of the drag models could be 1/2 the coefficient of drag, the cross-sectional area, the density of the fluid that it's going to be going through, which in our case is going to be air, and it could be a velocity-dependent model, or it could be a velocity squared dependent model. So I'm going to write that down over here. Velocity squared. All right, what I explained the other day in the notes is that if you parentheses these things, that you can just take all of those constant values and turn them into a variable, a constant variable, I'll say k. Or sometimes they use b, or sometimes they use anything that they want to use. All right, so kv squared. So basically, I'm choosing between one of these 2 models. Which of these best described my coffee filters? So let's talk about dropping the coffee filters or dropping something. So if I dropped, I'll just say a wad of paper. So here's my wad of paper like this. Wad of paper. So I turn my paper into a dot, and so my wad of paper would have an FW, and I'm going to make the drag, like the friction acting on my wad of paper as it's falling, equal to FW. So what's important to know is that if FW equals the drag, then I know that my wad of paper is not accelerating as it falls. Instead, it is now at terminal velocity. So I could say that when you reach terminal velocity, and this is a lowercase v, but with a capital T, That stands for terminal velocity. So when something has reached terminal velocity, it is no longer accelerating, and we know that Fw equals Fd. Well, why that's important to me is in this lab, we're dropping coffee filters because we know they will reach terminal velocity very quickly. And that's what we want, because if they're at terminal velocity, then I can replace the Fd with an mg. So really then my first model could be written like this, and my second model could be written like this. So as long as I am at terminal velocity, I can choose between model 1 or model 2. So let's focus on that part for a minute so we make sure that you understand that. So I'm going to pretend that I am going to the top of a really tall cliff. And let's drop a tennis ball. So here's a tennis ball. So as I drop the tennis ball, it would get farther and farther apart because it would be accelerating. And if I made a graph of the distance and time as it falls, I would say, well, the tennis ball is going to be accelerating for a period of time. So acceleration would be like a parabola. But then the tennis ball is eventually going to hit terminal velocity, and then it's going to start to go at a constant speed. So I'll just kind of section this off so you can see it a little bit better. So this was the time when it was accelerating, and this was the time that it was going at a constant velocity. And because it was accelerating and then started going at a constant velocity, this must be its terminal velocity that it kept falling at. So that would be true for like a tennis ball. So even though that's true, that model doesn't help me do this lab. But instead, what I did is, normally I would have you stand on the tables at school, but instead I went out to the garage at my house and I got a ladder, and you can see the picture in Blackboard there. But I got a ladder, and instead I reached my hand out, and by the way, I knew the height of my ladder. The height of my ladder is, I'm going to look it up here real quick. The height of my ladder was 1.914. So distance equals 1.914. That's how tall my ladder was. And I instead dropped coffee filters. So I'm going to draw a little coffee filter up here. All right, but technically what I did is all 7 of the coffee filters are nested in here. So I'll kind of like draw 7 of them all kind of nested. So when I dropped a coffee filter, it kind of like fluffy fell to the floor. And so why that's important is if I drew a graph now of that, of the coffee filters falling to the floor, the distance time graph, they probably accelerated for just a smidge, so like this, smidge, but then they reached constant velocity. And so this graph looks very different than this graph. So this graph, we're going to just make an assumption that really, for all practical purposes, as soon as I let go of those coffee filters, they reached terminal velocity. So because I don't have this little acceleration piece in here, I can just say, like, I'll make up easy numbers. If my ladder was 2 meters tall and it took 4 seconds to reach the ground, well, then my terminal velocity is 2 over 4.5 meters per second. So I can use just plain old distance over time to come up with the velocity because I dropped something that was very light so that I know that it's going to be at terminal velocity very quickly. Okay, I'm close to 10 minutes here, so I'm going to stop this video, and in the second piece, I'll give you the data and tell you what to do with it.